This video is about graphing trigonometric functions with some transformations involved. So if we look at y equals a times sine of b x minus c plus d, we have the following four things showing up for a, b, c, and d. A is the vertical stretch, which is something that is not really any different than any other function that we've done all year. Uh, and likewise with D being a vertical shift or C being a horizontal shift. Now, one thing that you will notice in this chapter when we're dealing with periodic functions, we call horizontal shifts phase shifts in this chapter. It's just a shift of where our cycle starts. So it's like where the phase of our cycle starts. So there's just a slight vocabulary change, but it's still a horizontal shift. And then B represents a horizontal stretch, which in essence, for periodic functions or trig functions, changes the period. Now, we also could have put something like y equals a times cosine b x minus c plus d, or tangent, cotangent, secant, or cosecant. All of these things do the exact same thing to the basic function, but they end up shifting it in a variety of different ways. And so our job in this video is to try and figure out what happens in all of these. So let's take a look at problem one. Y equals 3 times sine of 2x plus 2. So this 2 represents the vertical shift. So we're going up 2. The phase shift in this problem, there is none, and that's because we don't have a plus or minus on the inside of the function. The amplitude represents how much the vertical stretch is in this case, and so there is a vertical stretch of 3. The period of a sine graph, like we learned last time and in class, the period of a typical sine graph is 2 pi. And that's true for sine, cosine, secant, and cosecant. So the typical period is 2 pi. However, this 2 on the inside, the 2 times x, that adjusts the period. And what we're going to do in order to figure out what the period of any sine, cosine, secant, cosecant, tangent, cotangent graph is, so we're going to take the typical period and divide it by b. So in this case, the typical period for sine is 2 pi. And then we're going to divide it by 2 because in this problem, 2 represents b. So the period is pi. The domain of any sine function is negative infinity to infinity. And then the range is normally negative 1 to 1, but in this case, we had a vertical shift of 2. So that means our midline is 2. And then we will go up to 5 and down to negative 1 because that's what happens when your amplitude is 3. So our range is negative 1 to 5. So now what I'm going to do is I'm just going to graph a typical sine graph. So it starts at 2, goes up to 5, comes back to 2 in the middle, goes down to negative 1, and then comes back to 2 at the end. When we're doing this, what I notice is that there was no phase shift. So that means the x value is 0 at the start. And then now my normal period is 2 pi, but in this case, I have a period of pi. So what I have to do is I have to figure out where all of the major points are. So like all my maximums, minimums, and then spots in the middle where it hits the midline. And so normally what I will do is I will take my period and divide it by 4. And that will give me how much I add for every interval. So in this case, the period is pi. So pi divided by 4 is how much I add. So I started at 0, and then I'm going to add pi over 4 every time. So I'm at 0, then pi over 4, then 2 pi over 4, which I can reduce to pi halves, then 3 pi over 4, then 4 pi over 4, which I can reduce to pi. So I have now graphed my first sine function. So when I graph the function, it kind of looks like every other function that we've ever graphed for sine. I basically make it look exactly the same. But those functions are not actually exactly the same. If you zoom in on one particular cycle of the function and then just rearrange where the x and y values go, they actually do look identical if you're kind of zooming in on the graph where you want. And so basically, that's what I'm doing when I do these problems. I zoom in on where I want, and then I kind of write the x and y values that are associated with it. So while this is not exactly the same as y equals sine of x, if I zoom in on a certain part, it does look identical. And that's kind of what those Desmos graphs were supposed to kind of show you there. Y equals 3 secant x minus 2. So right now we're going to go a little bit faster. The vertical shift is -2. The amplitude is 3. There is no phase shift. Again, the period of a typical secant graph is 2 pi, and we do not have any reason to change this period because there's no b value in this problem. So the period is 2 pi. The domain is, well, the domain of a secant graph is a little interesting, and the range, we'll get to that in a second. So we'll talk about those in a little bit. Now, secant is really the reciprocal of cosine. So if I look at what a cosine graph might look like, I'm just going to graph what this would be if it was cosine. So if it was cosine, I have a vertical shift of 2. So I'm going to start at -2, and then I'm going to go down to -5. Then I'm going to go up to 1. And then cosine starts at the top, goes down, and then comes all the way back up. So that's kind of what cosine looks like for one cycle. But this is the reciprocal of cosine. So basically what I want to do, I need to make sure that I put my period. So 0 period is 2 pi divided by 4 to get my interval. So I add pi over 2 every time. So 0, pi over 2, pi, 3 pi over 2, and 2 pi. So that's kind of where all my x values go. Now, remember, I'm graphing the reciprocal of cosine. So what I have to do basically is I have to realize that anytime I'm at the midline, so in this case pi over 2 or 3 pi over 2, anytime I'm at the midline, that's kind of like this function being 0. So if I subbed in pi over 2, I'd get 3 times 0 minus 2. So I'm basically ending up with this secant thing being, the cosine being 0, which means the secant is undefined. So at pi over 2, the secant is undefined. So, what happens if it's undefined is we end up putting an asymptote. So I'm going to put an asymptote here, just like I did back in first semester when we were doing functions with rational functions. And then last chapter when we were doing logs and exponentials, we have some asymptotes. Now what I'm going to look at is if I sub in a value and cosine is 1, then secant will also be the exact same thing because the reciprocal of 1 is 1. So if I look at the very maximum and minimum values on my graph, they are going to be exactly the same as the cosine value. And then as I get close to 0, so as I get close to 0 on the cosine graph, what's going to happen is I will get closer to infinity on the secant graph. And so essentially, that's graphing one period of secant, I will just take cosine and turn it into a secant. I want to make sure that we see what it looks like in the grand scheme of things on Desmos, just so that we don't get confused. So this would be what the graph would look like, and it keeps going forever because it's a cyclical periodic function that goes forever. Secant basically takes this cosine and then it does all the reciprocals. So as we approach this dotted line where it represents 0, then all of the secant functions end up going off to infinity. So notice that the purple graph goes off to infinity at those cases. So even though when we're graphing it, it kind of looks like it just stops abruptly with the red, that's not actually happening. It's not really stopping abruptly. It's just we're only graphing one cycle. Okay, the rest of these we're going to go real fast because we took our time on the first two. Y equals 5 cosine x minus 2, vertical shift minus 2, phase shift none, amplitude 5, period is 2 pi because there's no change in that. Domain is negative infinity to infinity. And the range is, since we had a vertical shift of 2 and an amplitude of 5, that's going to be negative 7 to 3. Now, real quick, let's go back to the domain and range of that secant problem. The domain is actually all real numbers, except we have certain values that it doesn't work. Pi over 2, 3 pi over 2, 5 pi over 2. If I went in the other direction, negative pi over 2, negative 3 pi over 2, they wouldn't work. So in this case, the domain is all real numbers except anything that ends in a pi over 2. So the way that you would write that is k pi plus pi over 2, where k is an integer. Because if you plug in any integer value for k, you'd end up with 0 would give you pi over 2, 1 would give you 3 pi over 2, negative 1 would give you negative pi over 2, and so on. And then the range would be negative infinity to negative 5 union 1 to infinity. So it's a lot harder to write the domain and range for a secant or a cosecant problem. Okay, let's do cosine. So this is negative 2. If I go up by 5, I get 3. If I go down by 5, I get negative 7. Cosine starts at the top, goes down, and then comes all the way up. There was no phase shift, so that means this is 0. Pi over 2, pi, 3 pi over 2, and 2 pi for our main points, because remember, 2 pi was our period. We divided it by 4, so I add pi over 2 every time. Problem 4. Y equals secant times pi over 2x. There is no vertical shift. There is no phase shift. The amplitude would be 1 if we were dealing with a cosine graph. But since we're doing secant, it's actually going to be a little bit different. Amplitude is kind of a weird word to use with secant. The period, well, the normal period of secant is 2 pi, and we are going to divide by b. So pi over 2 is b. So if I divide by a fraction, I can multiply by the reciprocal. The pi's would cancel, and I end up with 4. So the period is 4. Well, that's kind of strange. We'll talk about that in a second. The domain is all real numbers except where k is in the integers, and we have, well, I guess we should actually figure out where those go in a second. The range is easier. That's from negative infinity to negative 1, union 1 to infinity. Okay, so we have y goes from negative 1 to 1. I'm going to graph cosine as a dotted line or a dotted curve, because really that's not what I actually want. So there was no phase shift. The period is 4. So if I do 4 divided by 4 to get my intervals, I add 1 every interval. So I have 1, 2, 3, 4. So that will help me. Notice that all the odd integers are going to be my asymptotes. 1, 3, and so on, because all of those things are where it crosses the axis. Now, I'm going to finish this graph by graphing secant, just like we did last time. So that's basically what my secant graph looks like. Number 5, -2 times cosine of 3 times x minus pi over 2. There is no vertical shift. The phase shift appears to be pi over 2 to the right, or plus pi over 2. The amplitude is 2. Notice that we have a -2 there. But even though it's negative, that doesn't change the amplitude. It's just going to change how the graph looks. It's going to be vertically flipped, essentially. So instead of cosine starting on top, it's going to now start on the bottom. And actually, my graph looks pretty good there, so I'm not going to erase it and do it again. My period is normally 2 pi, but I'm going to divide it by what my b is. So my period is 2 pi over 3. The domain of this function, it's a cosine function, so that's -infinity to infinity. And the range of this function is normally -1 to 1, but my amplitude is 2 in this case, so it's going to be -2 to 2 because there was no vertical shift. So it's going to kind of look like this. And then I need to figure out what my y values are. So there was a phase shift of pi over 2 to the right. So notice that this x value that I'm putting here is pi over 2. I'm actually shifting the whole graph. Now, some people will just start the graph here and call this pi over 2. But I kind of like to graph the exact same thing every time and not really mess around with it. So that's pi over 2. And now I have to figure out what I'm going to add every time. So 2 pi over 3 divided by 4 gives me 2 pi over 12, which is pi over 6. That's how much I add every interval. So I'm going to add that, pi over 2 plus pi over 6. This ends up adding fractions, and so maybe the best way to go about it is to convert everything into sixths. So if I think about pi over 2, that's the same thing as 3 pi over 6. So I start at pi over 2, I add pi over 6, that ends up being 4 pi over 6, which I can reduce to 2 pi over 3. 4 pi over 6 plus another 1 is 5 pi over 6. Plus another pi over 6 gives me 6 pi over 6, which I can reduce to pi. And then I add another one and I get 7 pi sixths for my final spot. Last problem that we're going to do, -7 cosine pi eighths x minus 2 plus 3. So we're dealing with all different types of shifts. We have a vertical shift up 3 or plus 3. We have a phase shift right 2 or plus 2. So that's where that comes from. The amplitude is 7, but we're going to start at the bottom because we have a negative cosine. The period is going to be 2 pi divided by b. So b is pi over 8. Remember, that's the same thing as 2 pi times 8 over pi, which is 16. So my period is 16. Notice that just like in the last problem, I don't know why that 2 got erased, sorry. But just like in the last problem, our period, our x values don't deal with pi's in this problem. Then, in order to figure out what I'm adding every time, I'm going to add 16 divided by 4, because I take the period and divide it by 4. So I add 4 every time. So I start to the right 2. So my x values start at 2. Then I add 4 every time. 6, 10, 14, 18. So that is kind of what one graph of this looks like. I have a vertical shift up 3. So my y value at my midline is 3, and then I subtract 7 and add 7 to figure out what that is. So range goes from -4 to 10, and the domain is -infinity to infinity.